So we're going to look briefly at the electromagnetic spectrum before we start looking at interference. We started off looking at sound waves, and these are of the order of 10 to the 3 meters. So we're talking thousands of meters, tens of meters, 100 meters, which is why radio antennas are so large. When you start getting down to microwaves, then we're talking centimeters, which is why if you look at a microwave grill, they normally have a little grill on the front plate, which is around about centimeter length, and that's just to stop the microwave radiation coming out and damaging our eyes. If you go even lower, then you start getting into the infrared, which is micrometers, so 10 to the minus 5, 10 to the minus 6, and certainly in the micrometer range and the nanometer range is our visible light. So we would talk about visible light as being about 500 nanometers through to about 800, 900 nanometers, this region here. And that's all we can see, this part here. Below that, you get ultraviolet, which is in the order of 10 to the minus 8, so nanometers and tens of nanometers, and then X-rays and gamma rays. And you can see from the approximate scale, these little pictures underneath, that's kind of like the scale of the types of atoms or the types of objects that you might measure with these waves. And that gives you an idea of why you might use X-rays to look at atoms, or why gamma rays are important to look at atomic nuclei. It's because they have the same wavelength as the object you're trying to measure. Having a look at our visible light, as we said, it's of the range of about 750 nanometers through to about 350. That's violet through to infrared. And if you have a mnemonic device that you kind of remember, red, orange, yellow, green, blue, we actually have one which we call Roy G. Biv. So red, orange, yellow, G, green, blue, indigo, violet. And that's because we have a little indigo in there. What use is this? Well, we see everything in colour. We don't see anything else. So when we looked at our diffraction grating, we had an image of all the colours that came off from the diffraction grating. CDs in particular are of the same order of diffraction gratings, but instead of actually looking at the light that's transmitted, as you might through a diffraction grating, you're actually looking at the light that is reflected. So a CD is a perfect reflection for that, and the various wavelengths are reflected at different angles, which means that you get a range of colours depending on what angle you view your CD at. And that's important in other ways. If you're looking at thin films, for example, or even any colours, what you're actually seeing is only the colour that is reflected from a surface. So, for example, a red object reflects red light because the red surface absorbs all the green and the blue light, so it's not reflected. And we're going to look at the conditions that give this sort of reflection. Before we do this, though, I want to look again at reflection of waves from a boundary, because we talked about it when we were talking about strings. We have these pulses that travel along a string. But what happens when they hit something? Well, if they hit a hard boundary, then the string travels along, hits the boundary, and is reflected, but it undergoes a phase change, a 180-degree phase change, which is basically can be thought of as a Landau on 2 or half a wavelength change in displacement. If you have a soft boundary, then the phase change doesn't occur because the endpoint is free to move. And what we actually think about is actually not these types of boundaries, which we can consider the phase boundaries, but what actually happens when you're actually going through various materials. So, for example, if you go from a high speed to a low speed material, so let's look at what happens when a wave is going into a different medium. So if we consider this boundary here between a high speed and a low speed medium, so for example a low density to a high density, so for example from air to water or air to oil or that sort of interference, then once you go from a low density to a high density, you get this phase reflection. You also get transmission, and the transmission keeps the same phase. What do we see? Well, the amplitudes of the reflected and the transmitted phase are not the same. You can see that they add up to be the same as the initial amplitude, but some of it's reflected as, with the phase change, and some of it is transmitted. So let's look at a wave being transmitted from a low density to a high density, so from air into water. You can see that there's a phase transition at this boundary. The reflected wave is 180 degrees out of phase, so it's inverted, while the transmitted wave goes straight through. And this is what happens when you see various light waves that are incident on that sort of boundary. In the opposite direction, from a high density, such as water, to a low density, such as air, there is no phase transition. And this is important. We're going to come back to it in our work. Thin film interference occurs in films such as soap bubbles or oil on water, or even in the back of a butterfly's wing. All of these situations, all of these surfaces show colourful patterns known because of thin film interference. And it's basically the interference of light waves reflecting off the top surface of a film with the waves that are reflecting from the bottom surface. So that interference is either constructive or destructive. To obtain a nice pattern, the thickness of the film has to be similar to the wavelength of the light. And another important consideration in determining whether the waves interfere constructively or destructively is the fact that whenever the light reflects off the surface of a high index of refraction, the wave is inverted. That means it's a phase shift. The peaks become troughs and the troughs become peaks. It's referred to as a 180-degree phase shift in the wave, but the easiest way to calculate it and use it is to think of it as an effective shift in the wave by half a wavelength. So to summarize this, reflective waves experience a 180-degree phase shift or half a wavelength when reflected from a higher medium to a lower medium, higher density to a lower density. So where N2 is greater than N1. But there's no phase shift when reflecting from the medium of a lower index of refraction, for example, when N2 is less than N1. So for completely constructive interference to occur, the two reflected waves must be shifted by an integer multiple of wavelengths relative to one another. This is the condition for constructive interference that we've always had, n lambda. This relative shift includes any phase shifts that are introduced by reflections of a higher index of refraction medium, as well as the extra distance travelled by the wave that goes down and back through the film. And one has to be very careful when dealing with wavelength because the wavelength depends on the index of refraction. As you know, the wave slows down as it hits the medium and the wavelength becomes larger. So if the film has an index of refraction, the wavelength is related to the wavelength in the vacuum by a condition where lambda of the film is equal to lambda of the vacuum divided by n, the index of refraction. I'm going to give you a step-by-step approach on how to solve problems for thin film interference. The diagram that we're giving you now is a typical arrangement for thin film interference. You have incident light, which is reflected from the top surface and also reflected from the bottom surface. And there might be three various materials. Usually the first one might be air, but it could be anything. So N1, N2, and N3. And the overall goal is to figure out the shift of the wave reflecting from one surface of the film relative to the wave that reflects off the other surface. And this is the condition for constructive interference or destructive interference, depending on what you see. So most problems involve normal incident light. So you're basically looking at the film from perpendicular. The light rays are not drawn perpendicular because otherwise you wouldn't be able to see anything. There'd just be light going in, light going out, you can't see it. So they tend to be drawn at a slight angle, but it's assumed that the incident and the reflected rays are actually perpendicular to the interface. So here's the steps for analysing. Step 1, write down the shift for the wave reflecting off the top surface of the film. This is basically, is there a phase shift? And there will be a shift if the index of refraction of the first medium is greater than the index of refraction of the second medium. The shift will either be 0 if N1 is greater than N2, or lambda on 2 if N1 is less than N2. So the relative shift is either 0 or lambda on 2. And then you need to work out the shift for B, which is the second medium. So this is off the second interface. That's step 2. That's the shift for the wave reflecting off the film's bottom surface. So one contribution to the shifts comes from the extra distance travelled. So if the film thickness is T and the wave goes down and back through the film, its path length is actually longer by 2T because it's got to go down and then back. The other contribution to this shift can also be either 0 or lambda on 2, depending on what happens when it reflects. So if N2 is greater than N3, then you're going to have 2T, which is just going down and back and no phase shift. But if N2 is less than N3, then you're going to have 2T, so 2 times the thickness, plus lambda on 2, so an extra phase shift. So then you calculate the relative phase shift by subtracting the individual shifts. So your relative phase shift delta is equal to delta B minus delta A, and that's step 3. Step 4 is then setting that relative shift to the condition for constructive interference or destructive interference, depending on the situation. So for example, if a certain film looks red in reflected light, that means that it has to have constructive interference for red light. If a film is dark, then a light must be interfering destructively. So remember, for constructive interference, that delta should be equal to m lambda, and for destructive, it'll be m plus a half times lambda, where m is an integer number of wavelengths. So then you rearrange all your equations to get your factors of lambda on one side and include your t on the other side. And remember that the wavelength that you have in your equation is the wavelength in the film itself, and that is dependent on the index of refraction. So remember, the lambda 2 is equal to lambda of the vacuum divided by n2. And again, if you have to use a similar condition for the third interface. And then you should solve it. Step 7. The equation should give you a relationship between the film thickness and the wavelength in vacuum, or the wavelength in the film.